All right. Yesterday we finished up with electronegativity, the ability to attract an electron. Good. As we go across the period, electronegativity increases because? Nice. And as we go down a family? Because?
Distance.
Yeah, distance from the nucleus. The valence shell gets further and further away from the nucleus. Very nice. All right. Last one. Electron affinity. Electron affinity. All right. Now, I got two analogies for electron affinity. I love electron affinity. It's one of my favorites. All right. By definition, electron affinity is the energy associated with gaining an electron. Okay. The energy associated with gaining an electron. The equation that we normally write for electron affinity goes like this. You take neutral atom A, and you're going to add to it an electron. Well, what happens when I take a neutral atom and give it an electron? What charge does it obtain? Yeah, negative. It becomes a negative ion, or an anion. So we get A with a negative charge, and electron affinity. And when you talk about electron affinity, you normally talk about it being given off, a negative charge. But I'm going to give you an example when electron affinity will be a positive value. Okay? A positive value of electron affinity. Let me give you the analogy of electron affinity. I love electron affinity just because of this story. This is one of my favorites. All right. I like to make an analogy between the halogens and its electron affinity and a little kid in a grocery cart. Yeah, it's one of my favorites. All right. You know, moms take their little kids. Where do they put them? Right in that little seat, right? So they're about this height, right? In the grocery cart. They're riding along, yay! And then all of a sudden, Mom gets stuck in what I like to call the cashier canyon. All right? She pulls her cart in, and what do you have on both sides of you? Junk food. Lots of candy and good things. And at what height? Right at eye level height for the little kids, right? You think that's a mistake? No. That's a marketing ploy. Go talk to Miss Fisher. She'll tell you. They purposely put candy and all that good stuff right at eye level. Think about the cereal aisle in the grocery store. The healthy stuff all the way on the top where the adults can reach it, right? The generic stuff all the way on the bottom, you know, nobody wants to talk about. But where are the ones with the cartoon characters and all the fruity things and lots of sugar? Right at eye level again. Why? Because when the little kid sees it, they're like, I want it, right? They're sitting there going, ah! So what does Mom do? Mom takes out and says, here. And what does little kid do once he gets his candy? He goes, right? That's the analogy that I like to use to the halogens. And they want an electron really, really badly. And they've got all this energy, and they're like, I want it. As soon as they get it, they become a lot more stable, and they calm down, and they give off all that energy. That, folks, is electron affinity. Make sense? We good? All right. So electron affinity, when you discuss electron affinity, you usually discuss it with the atoms that want an electron and how much energy is given off when they obtain an electron. They give off lots and lots of energy. Why? What's the goal of all atoms? They want a full valence shell. And when they get it, they're a lot more stable. And that's why they give off that energy. And that energy is called electron affinity. So far, so good. However, if you check out the electron affinity chart, it ends right at the halogens. The noble gases are not on the electron affinity chart. Now let's talk about why. Here's my second analogy. Who here has pets? Cats? Dogs? Yeah? Do you ever have to give your cat or your dog some medicine? They sit there and they go like this. I don't want any medicine. They're gritting their teeth and they hold their jaw clenched, right? And you're trying to give it medicine. He won't open his jaw, and you got to force him to open it up, right? You got to add energy to get them to open up the jaw so they'll take their medicine. Noble gases are like that analogy. Why would noble gases have to be forced to take an electron? They already, yeah, that's it. They already have a full valence shell, right? So you have to force them to take an electron. So guess what their electron affinity is? If you've got to force it and you've got to add energy to make them take it, what are you going to do? Positive electron affinity, right? And that's why when you see an electron affinity chart, the one family that's missing are the noble gases, because you don't want to talk about it. Because electron affinity in general is a negative value. Energy given off when an atom takes in an electron. Why? Because its valence shell is now full and it is more stable. Are there any questions? So let's talk about the trend. Here we go. So in general, remember we take a periodic chart. And in general, as we go across a period, what happens to not the sign, don't think of it the negative as getting more negative. Think of it, the quantity of energy is getting bigger and bigger and bigger. The negative just means it's being given off. Everybody okay with that? All right. So as we go across a period, it increases. Why does electron affinity, the amount of energy given off, increase as you go across a period? Because you're getting closer to a full outer shell. Why does it decrease as you go down a family? Because the valence shell, where you're going to add that electron, is getting further away from the nucleus. End of story. Sounds like a repeated pattern, doesn't it? Absolutely. Absolutely. All right. So, in summary, here's a picture of the summary. And I want to relate it to some vocabulary that you may see on Dr. Goldie's exams. What this shows you are the characteristics or the properties that increase going to the upper right-hand corner in this area here, okay? The property that increases down in this corner is atomic radius. That's why it points this way, okay? Thanks, Sam. All right, so the two vocabulary words that you may see associated with this idea is metallic character and non-metallic character. Metallic character and non-metallic character. Now, metallic character means characteristics of a metal. So what are some of the dominant characteristics of metals? Think about it. What do metals like to do? This is section 8.7, by the way. Part of it. What do metals like to do? Oh, come on. What do metals like to do? They're metals. What do you use metals for? They're good conductors. Ah, there you go. They're good conductors. They're shiny. Okay? They like to lose electrons. And if you were to pick the epitome of the metals, that means like the role model. Who does it the best? That location is right here, okay? That location is in the lower left-hand corner. That would be like the most metallic element. Down in the left-hand corner, did I say right? Yeah, down in the left-hand corner. That's the most metallic metal. In other words, that is the one element that displays the characteristics of a metal the most, or the best. Opposite of that, in the upper right-hand corner, over here, are the epitome of the non-metals, meaning they display, well, with the exception of the noble gases, so let's take that one out, and let's circle fluorine, okay? Fluorine is the most non-metallic element. The most non-metallic element. If you had to pick the epitome of an element to represent the non-metals, it would be fluorine. Loves to gain electrons, right? Okay? Isn't shiny. You know, everything you could go through in terms of your non-metallic characteristics over there. High ionization energy, high electronegativity. Okay, that kind of stuff. So as you progress to the upper right, as you go this, you increase your non-metallic character. As you progress down to the lower left, you increase your metallic character. Are there any questions? All right.